Welcome to control system classes. The next topic for discussion is poles, zeros, order and type of the system. As these parameters are necessary, you need to understand to discuss about the stability of the system. Let us define about the order of the system. So we can define order of the system by looking at the value of n. Here, m represents the highest degree of numerator and n represents the highest degree of denominator polynomial. When n is equal to 0, the highest power is 0. So s bar 0 is 1. We can call it as a zero order system. We can call it as a zero order system. When n is equal to 1, we can call the system as first order system. When n is equal to 2, we'll call the system as second order system. So the highest power of the denominator polynomial is called as the order of the system. The degree of denominator polynomial is called as order of the system. So like that way we can able to define the order of the system. What is the necessity to discuss about the order of the system? As order decides about the stability of the system. So when the order increases, the complexity of the system also increase and the instability problem will also increase. So the order is an important term. The second term we are going to discuss is poles and zeros. So here a transfer function is given represented as h of s and it has a numerator polynomial with highest power as m and the denominator polynomial with highest power as n. And the numerator is factorized and denominator is also factorized. So the roots of numerator are called as z1, z2 and so on up to zm. So the denominator roots are called as p1, p2 up to the value as pn. So these are the roots of numerator as well as the roots of the denominator, right? Where k is maybe a gain or a constant, right? So let us define poles and zeros. So what is a pole? So we can define a pole as the roots of the denominator. The poles are nothing but the roots of the denominator. For example, what are all the roots here? P1, P2 up to Pn. They are the roots of the denominator. So when we substitute the poles P1, P2 in the place of S, so the total transfer function will become infinite. That's why they are called as a pole. So in the equator pole, we don't know the equator pole where it ends. It ends in infinity. Similarly, when we substitute this value P1, P2, P, any value when you substitute for S, in place of S, the transfer function will take a value as infinity. That's why they are called as poles of the system. So let us define zeros. So if you want to define zeros, we need to concentrate about the numerator. So the roots of numerator are called as, the roots of numerator is called as zeros. So what are the roots we got here? The roots are z1, z2 up to zm. So when you substitute in place of s with zero values, that is z1, when you substitute s as z1, the total transfer function will take a value of 0. That's why it is called as zeros of the system. As it makes the overall system response as 0, we'll call it as a zeros of the system. So the roots of numerator that drive the system response to 0 is called as zeros of the system. It is called as zeros of the system. Let us discuss with a simple example. H of s is s plus 2 divided by s plus 8. So what are all the roots of numerator? S plus 2 equated to 0 will give s is equal to minus 2. So s is equal to minus 2 is called 0 of the system. Since when you substitute s as minus 2, the total system response will become 0. When you substitute s as minus 2, the total system response will become 0. So the roots of denominator that drives the system response to infinity. So when denominator is equated to 0, for example, in the above case, s plus 8 equated to 0, it will become s is equal to minus 8. And when we substitute s as minus 8, so the system response will become infinity. And hence it is called as pole of the system. So poles and zeros are important terms. It decides the magnitude of oscillations and the concepts about stability. Type of the system. So how to define the type? Let us define the type. For example, h of s is s plus 8. So what is the value of pole? The pole is s is equal to minus 8. The pole is s is equal to minus 8. So when s is equal to minus 8, we have one pole at s is equal to minus 8 and no pole at origin, and hence the system is called as type 0 system. In the next case, 1 divided by s square into s plus 8. So it is a type 2 system. So here totally we have 3 poles and 2 poles. One pole is at minus 8 and 2 pole is at origin, and hence the system is called as type 2 system. So how we can define type of the system? So we can define the type of the system as the total number of poles that present at origin. The total number of poles that present at origin will decide the type of system. Static error constants. There are three types of static error constants. They are called as positional error constant, velocity error constant, and acceleration error constants. So Kp is limit s tends to 0, g of s into h of s. As velocity is the next order derivative, so s into acceleration, s square into g of s, h of s. And then we know that when type increases, the Kp, Kv, Ka value becomes infinite. When type increases, the error constant increases. When type increases, the error constant increases. What is the formula of steady state error? Then for unit step signal, the steady state error ESS is 1 divided by 1 plus Kp. When input is unit step signal, the steady state error is 1 divided by 1 plus Kp. For unit ramp signal, ESS is 1 divided by Kv. For unit parabolic signal, ESS is 1 by Ka. Similarly, when substituting the value of Kp by referring the first table in the formula, we got the error as like this. So we can conclude that when type of the system increases, the error decreases. When type of the system increases, initially it is constant 0. Initially the error is infinity, then constant, then 0. Infinity, infinity, constant, then 0. So when type increases, the steady state error decreases. So here when type increases, the error constant value magnitude increases. Final conclusion is when type of the system is increasing from 0, 1, 2 and 3, the unit step signal, the error decreases. For unit ramp from infinity to 0, for unit parabola from infinity to 0. These values are constant values. So the conclusion is if type number of the system increases, then steady state error ESS decreases. So we calculated ESS. The other formula of error signal in S domain is E of S is equal to R of S divided by 1 plus G of S, H of S. And from the final value theorem, we can write ESS as limit t tends to infinity, E of t is equal to limit S tends to 0, S into E of S. So we can substitute E of S from the formula. Whereas if we know E of t, we can directly solve ESS. What is E of t? E of t is nothing but R of t minus C of t. R of S is reference input in time domain. C of t is the response in time domain. So either way, what information we can have in the hand, based on the given data, we can able to find the other parameters. Thank you. In the next thing we will discuss about the controllers.